The average American drives about 35 miles per day. So how many solar panels would you need to cover your commute? Well, it depends. It depends on what car you're driving, the type of climate you're going to be driving in, what size solar panels, the
efficiency of those panels, the location of the panels, does your wifey want you to have panels, the tilt of the panels, the azimuth of the panels, the month of the year that the panel's going to be working on.
But I'm going to keep this simple. I'm going to make some assumptions, some averages based on scenarios I see the most. Let's say you have a Tesla Model 3 and you live in Southern California. During the summer, it will take about 227 watt hours to drive 1 mile. So 35 miles times 227 watt hours equals 7.945 kilowatt hours per day. In the winter, the same car is going to be less efficient, 317 watt hours to drive 1 mile. That means our 35-mile commute times 317 watt hours is going to equal to about 11.095 kilowatt hours a day in the winter. Now let's talk about the sun. In Southern California, in the summer, we get an average of 6.5 hours of peak sun. But in the winter, we only get about 3.8 hours of peak sun. Now let's talk about solar panels. I'm going to use a Tier 1 440 watt panel. Now we must account for inverter conversion loss to about 2 to 5% to switch from DC solar to AC for your car. We must account for thermal heat loss, wiring resistance, and some dirt on the panels. And if you add everything up, we're looking at about 16% conversion loss. If you're charging your car at night after work, you probably have a battery. I'm going to use a Tesla Powerwall 3 for this example. And the established RTE for a Powerwall 3 is at 89%. So to find the net efficiency from your solar system to the battery to your EV, we must multiply the 84% times the 89% and you'll get a 75% total efficiency. Okay, time for the results. In June, we need 7.95 kilowatt hours. We divide that by the 75% efficiency rate times the 6.5 hours of peak sun and you'll get 1.67 kilowatt hours needed. So we have 1,630 watts divided by 440 watt panels equals to 3.7. So we round up to 4 panels. In December, we need 11.1 kilowatt hours of energy. We divide that by the 75% efficiency rate times the 3.8 peak sun hours, and you'll get 3.89 kilowatt hours needed. So we have 3,890 watts divided by 440 watt panels, you'll get 8.84 panels needed. So we round up to 9 panels. So there you go. 4 panels in the summer, 9 panels in the winter.